Hello everyone. So now we start with chapter 5, and chapter 5 is about integrals, and the general idea of integral is to find the total change or the net change. And so in section 5.1 we start by approximating areas. So the goals of this section are to first approximate areas between a curve and the x-axis on a closed interval. And we'll do this using rectangles. And secondly, we will also introduce Riemann sums. So this is a compact, well, this is a sigma notation sum. So let me also write sigma notation. So sigma notation is basically writing a large sum in a compact form, and Riemann sums are specific sums that actually approximate the areas under a curve or between a curve and the x-axis. So let me start by first reminding you of some very basic facts. So recall that if you have various shapes, we know how to find the areas of these shapes very easily. So for example, if you have a rectangle of base b and height h, then the area of such a rectangle is base times height. And if you have a triangle, so this is a triangle, and then the base is b and the height is h, the area is base times height over 2. And if you have, for example, a circle of radius r, then the area is pi r squared, and so on. So if you have basically some very easy shapes, let's say, then you can find the area of these shapes very easily. Now, what if you have the following scenario? Let's say you have the graph of a function y is equal to f of x, and then x is in some interval, closed interval a comma b. So let's say that the graph looks like this. Let me write this again. So let's say this is the graph, and this is a, and this is b. So now the question here is, how do you find the area of this region here? So the area of this region is the topic of this first section, and then later on we'll define this more precisely. So the question is, what is the area of the yellow region? Okay. Now to answer this question, we start by first doing the following. Well, instead of finding the area exactly, let's first try to approximate it. So let's first try to approximate this area. Let me copy and paste this picture first, because we'll need this. So what we will do is, let me magnify this. So what we'll do is the following. So we will take this interval a to b, and then we'll divide this into smaller pieces. Okay. Then for each piece we will construct some rectangles. So for each piece we'll have that as a rectangle. All right. So let me do this precisely now. All right. So let me divide a comma b onto, let's say, 4 rectangles. Okay, so I divide first of all the interval a comma b into 4 subintervals. Then for each subinterval, I construct some rectangles. So what I'm going to do is, first let me draw these dotted vertical lines for each point. And then I'm going to construct rectangles where the height of the rectangle, for example, let's look at the first one. The height of the first rectangle is going to be the value of the function on the right endpoint. Okay, so let's do that. So I'm going to construct this rectangle here. Okay, then I'll do the same for the second subinterval. So I'm going to choose this height, which is the right endpoint of this interval, as the height of the rectangle. So let me construct this rectangle as well. So this is the height. This is the second rectangle. And then we do the same for the other two as well. So the third rectangle will be this. And the fourth rectangle will be this rectangle here. Alright, so now we're going to say that instead of finding the area shaded in yellow, let's find the areas of these rectangles. And the area shaded in yellow is approximately, so maybe I should do the yellow a little better. So okay, just give me a moment. Okay, so if I'm finding the yellow area, I'll find the areas of the blue rectangles. All right, so then we will say that the area so the yellow area, which is basically the area between the function and the x-axis. So by the way, here I have the x-axis, here I have the y-axis, and here I have the x-axis, here I have the y-axis. All right, so this is approximately the sum of areas of the blue rectangles. Okay, and this is how we'll proceed. All right, so let me first do an example and then we'll proceed from there. Okay, so one example is the following. So let's try to do this whole procedure here using a specific function and specific values for a and b for the interval. All right, so let's approximate the area under the curve let's say y is equal to f of x, which is equal to x squared, from x equals 0 to x equal 2. All right, let's first draw the graph of y is equal to x squared. So let's say that this is the y-axis, and then this is the x-axis. So y is equal to x squared looks like this, more or less. Okay, and let's say that here is 0. 0 is the origin, and then 2 is somewhere here. Okay, so we want to find, or actually we want to approximate the area under this curve. And let's first use 4 rectangles. All right, so I'm going to divide this interval into 4 pieces, and I want them to have equal length. Throughout this section, all of the rectangle have the same base length. Okay, so the subintervals will look like this. So this is 1 over 2, and then this is 1 over 4, and this is 3 over 4. All right, so just like in the previous picture that I drew here, I'm going to construct rectangles on top of each subinterval. So this is the first subinterval, the second, the third, and the fourth subinterval. Okay? So I'm going to let me first draw these vertical dotted lines. And then I have these points here. And then for the very first interval, let me construct a rectangle where the height is the value of the function on the right endpoint of the interval. So basically this is going to be the height of the rectangle. So the rectangle is going to look like this. And for the second rectangle, I'll do the same. I'll choose this to be the height, and then I'll construct the rectangle. And then here is the height of the third rectangle. And then the fourth rectangle has this height. Okay, so now what I'll do is I'll find the area of these blue rectangles. So let me highlight them in pink. All right, so these are my pink rectangles finally. So the area of the first rectangle, let me give them names. So let's call this area A1, A2, then A3, then A4. Okay, so area A1 should be base times height. Maybe I should write this in black. Okay, let me erase this. So A1 is base times height, and then base is just 1 over 4 times the height is the value of this function at this point. So this is 1 over 4 squared. Okay, then area A2 is equal to, again, base times height. Bases have all the same length, so 1 over 4 for the base times now the value of the function, of this function here, at this right endpoint. So I should write here 1 over 2 squared, and I keep doing that. So A3 is again base times height, so this is 1/4 times the height, which is going to be 3 over 4 squared, and then the last one is base times height, which is 1 over 4 times 1 squared. All right, so the area under the curve y is equal to x squared is approximately so let me write this here. So the area under y is equal to x squared is approximately a1 plus a2 plus a3 plus a4. So area is approximately the sum of these values here. Okay, so let me write them down. So I have 1 over 4 times 1 over 4 squared plus 1 over 4 times 1 over 2 squared plus 1 over 4 times 3 over 4 squared plus 1 over 4 times 1 squared. Actually, you can write this as 1 over 4 times 1 over 4 squared plus 1 over 2 squared plus 3 over 4 squared plus 1 squared. And if you calculate this, you will find 3.75. Okay, so this means that this area so the area under the curve y is equal to x squared from 0 to 2. So this area right here is approximately 3.75. Now this calculation right here is also called R4 because we use right endpoints and 4 rectangles. Okay, so let me just say that we also denote the sum above by R sub 4 since we are using right endpoints and 4 rectangles. So basically, I think you got what I'm doing here. So you have this right here, and then this 4 here, and then you get R4. So this means that R sub 4 is equal to 1 over 4. And you have 1 over 2 squared plus, sorry, it should be 1 over 4 squared. Okay. 1 over 4 squared plus 1 over 2 squared plus 3 over 4 squared plus 1 squared. All right. So you could do the same thing now by using left endpoints. And let's see what happens. Okay. Let's do the same approximation using left endpoints. And 4 rectangles. All right. So what I'm going to do is I'm going to take this picture here and construct the rectangles using left endpoints. Okay, so let me do that. So maybe I need this one here, so let me copy this. What I need to do now is I need to erase okay. So now I'm going to do the following. So instead of using right endpoints, I'm going to use left endpoints. Maybe I should use the red color here instead. So for the first rectangle, So basically I'm using the first subinterval. I'm going to draw a rectangle whose height is the value of the function at the left endpoint. So the first rectangle is just a line segment. And for the second interval, I'm going to choose for the height, the length of the value of the function on the left endpoint. So I'm going to construct this rectangle. And I keep doing that. So for the third one, I choose this. And for the last one, I choose this. Okay. So basically, I don't need this part anymore. Right? And let's also change these and make them red. So let's say A1, A2, A3, and A4. Let's also change the highlight to, let's say, green. Okay. So then we have, oops, let's go back. All right, now of course, since the first rectangle has no height, there is no green highlight there. Okay, so let me keep going here. So the first area is equal to, again, base times height. So the base is, again, 1 over 4, and the height is just 0 squared. And then the second area is base times height again, which is 1 over 4 again, times, now you have to use the left endpoint of the second interval, so you have 1 over 4 squared, and then A3 is base times height, so 1/4 times 1 over 2 squared, and then the last one is A4, which is base times height, which is 1 over 4 times 3 over 4 squared. All right, so finally, let's add these numbers up. And by the way, this approximation is also called L4 because of the left here. So this left here and this 4 here. So we are also going to denote this by L sub 4. So the area is approximately L sub 4, which is equal to A1 plus A2 plus A3 plus A4. Okay, and this is equal to 1 over 4 times 0 squared plus 1 over 4 squared plus 1 over 2 squared plus 3/4 squared. All right, so if you calculate this, this is equal to let me just make sure. So this is 1.75. All right. Now, let me also make another remark here. So let's compare L4, R4, and the actual area. So as you can see from the pictures, in this green picture here, the approximated area is less than the actual area because there's some missing part here, here, and here, and here. Okay, and if you go back to the previous picture, when we're doing R4, there are some more things than what we need. So this is more than what we need. This is also excessive. So you have more area than what you actually have under the curve. So basically R4 is an underestimate, so R4 is strictly bigger than the actual area, but the left approximation L sub 4 is strictly smaller, so this is called an underestimate. And this is an overestimate. Okay. Now what happens in general? So in general, this is not always true. So this is not true for any function. What I've written here, this inequality is true for this specific function, and this for this specific approximation. So if you change the function and the type of approximation, this inequality might change. But let me tell you how to do this approximation in general. Okay, what happens in general? All right, so in general, if you have a function y is equal to f of x, well, let's suppose that this function is positive. Let's suppose that the domain in this case is a comma b, and f is nice on the interval a comma b. It's continuous and everything that we need. So then we can approximate the area between the curve and, so this is the curve, and the x-axis using rectangles. So to approximate the area under this curve, under y is equal to f of x on the closed interval a comma b, we proceed as follows. Okay, so the first step is to divide the interval a comma b into a certain number of pieces. Let's call this number n. So divide a comma b into n subintervals of equal length. Okay, so the length will be called delta x, and this is b minus a, which is the length of the interval, over n, which is the number of pieces. Okay, and moreover, if you do this, you have the following. So let's draw this a comma b and on the real line, let's say. So let's say this is a and then this is b. So you have many intervals here of the same length. And each of these points that I've drawn here are, so each of these points is an endpoint for some subinterval. So we're going to give them names. So this is x sub 0, and the next one is x1, x2, x3, and so on. The very last one is xn, because you have n subintervals, and the previous one is xn minus 1, and so on. So basically, x0 is the number a. This is always the first point in the closed interval. The next point is a plus delta x, because this length here is delta x. All of the lengths are the same. So x2 now is a plus 2 times delta x. Okay, and you keep going like that. So in general, x sub I is equal to a plus I times delta x, and the very last one is x sub n, which is b. All right. Now, the next step is to construct rectangles. Before I go to the rectangles, let me also talk about subintervals. So these intervals here are x0, x1 is the first one, x1, x2 is the second one, and so on. So the subintervals look like this. Okay, so the first one is x0, x1. The second one is x1, x2, and so on. The last one is xn minus 1, xn. So this is the first, this is the second, and so on. So this is the nth subinterval. So somewhere here in between all of these intervals, there is a generic one called the ith subinterval, and the ith subinterval has the form xi minus 1, xi. All right. And let's suppose that we choose some point, let me call this xi star, in the ith subinterval. So this is any point. This has to be fixed, okay? All right, so we'll need this in the next step. So now we're going to construct rectangles. So we're going to construct rectangles on top of each of these subintervals. So let me take this picture here again, because I need this. So let's copy this, and let's put this here. Okay, so now we have, so this is x1, x2, x3, x4, and so on. Okay, so we're going to construct a rectangle somewhere here. So let's pick this one. So let's say this is x. Say this is xi minus 1, and this is xi. Okay, so I have these 2 points here. Now we're going to construct a rectangle whose height is the value of the function on some point. Let me call this point here xi. Now xi is an arbitrary point between xi star is an arbitrary point between xi minus 1 and xi. So let's say this is the value of the function. So the height of this rectangle is going to be that value. So let me construct this rectangle. Okay. Now the area of this rectangle is base times height. So base times height, but the base is always delta x because that's the length of the subinterval, and the height is the value of the function at this xi star. Okay. So the last step is now to add all of these areas here. Then you'll have an approximation for the area of the region under the curve. So the area under, okay, so the area under the curve is equal to, or is approximately equal to the sums of all of these areas here. Okay, so the sums, say the sum of areas of these rectangles. So the area is approximately, so the very first rectangle has area delta x times f of x1 star. Then the next rectangle has area delta x f of x2 star. And then you keep going like that. So the very last one has area delta x f of x n star. Okay, now this is called a Riemann sum. And there is a more compact way of writing this area, which is basically the following. So the sigma notation, let me just say sigma summation notation. So if you write the sum I from 1 to n of, let's say, a sub I, this means a1 plus a2 plus a3 and so on up to an. So this means the sum of all these terms as this index I changes from 1 to n. Okay? So in our notation, the Riemann sum says that the area is approximately this sum here, which is equal to also, according to this new notation now, this is equal to the sum I from 1 to n. Now, note here that everything is the same. Delta x is the same, delta x is the same, delta x is the same. The only thing that changes is this index here. Okay, it goes from 1 to n. So we're going to write the sum of delta x f of x sub I star. Okay, and this sum here is exactly this sum here. All right. Now, what is the good thing about this sum? Now, of course, you can take the function y is equal to f of x, and then maybe do some rectangles. Let me just draw the function first. So if you have this function here, and you do, let's say, 4 rectangles, then you have these rectangles, right? So you have x1, x2, x3, then x0, and then xn. So if you construct rectangles, let me first copy this because I need this again. So let's copy and then paste here. So if you, let's look at the first picture. So if you use 4 rectangles, then let's say you use right endpoints for the heights. Then you're going to construct rectangles that give you an approximation for the area, right? So these rectangles here will approximate the area under the curve. Now you can also choose more rectangles. So maybe I don't need this this notation here anymore because this is going to be hard to write all down. But if you have more rectangles, if you have, let's say, 8 rectangles, then let me zoom in. You'll construct more rectangles, and actually, as you construct more rectangles, you have a better and a better approximation. So let me construct all of these. Right. So here you have some rectangles. Here you have more rectangles. So this is a better approximation. So if you keep doing more and more rectangles, the approximation is becoming better and better. So basically, as n goes to infinity, we are assuming that everything is nice. So as n goes to infinity, this sum here will approach the actual area. So the Riemann sum, I from 1 to n, I'd like to switch the order of delta x and put it back here. So let me do that, because that's what people use the most. So f of xi star delta x, this approaches the actual area. Okay, and this is going to be important in this class. So remember, L4 is sum with 4 rectangles and left endpoints, and R4 was sum with 4 rectangles and right endpoints. Okay, so in light of this Riemann sum here, let me define also, so remember this is the Riemann sum. We also define what Ln and Rn should be as a sum using the sigma notation. So in general, Ln is the following. So it's a Riemann sum, I from 1 to n, f of something, let me write that something later, times delta x. Everything is the same. Now the only problem, or the only, let's say, question with the Riemann sum is, what is this xi star? Okay, we don't know what that is. So if you choose it to be one of the endpoints, like the left endpoint or the right endpoint of the ith subinterval, then you have yourself a specific sum. So since we're using left endpoints here, then the left endpoint of the ith subinterval x is xi minus 1. So this should be xi minus 1. And if you write this out, you have delta x is the same for all of them. So you have to start with f of x0, and then f of x1, up to f of x n minus 1. So basically we start with 0 and end with n minus 1. So you don't really count xn. If you do the right endpoints, then instead of having xi minus 1 here, we're going to have xi. So f of xi delta x. So if you expand this, you have f of x1. So you start from 1. The next one is f of x2 up to f of x n. So here you don't really count x0. So for the left endpoints, you don't count the very last point. For the right endpoints, you don't really count the very first point. All right, so now you can use these equations to solve problems.